We know that in a lattice we have a unique greatest lower bound and least upper bound between any two elements of the lattice. We have seen that defines an operation that we called meet and join. So we will construct now a table of operations for each of these operators for the meet and for the join. Like a table of multiplication, say, we can have now a table of meet and a table of join. For instance, for the table of meet, we can complete this table with the result of the meet of each two elements. I mean, just looking at the Hasse diagram, we should be able to calculate what is the meet of any two elements. So, for instance, the meet between C and D is G. So we will write down this in the table. I mean, if we have C and D, we will complete here that the result is G, and so on. Have in mind to calculate the meet. The meet is the greatest lower bound. So, for instance, let's start with AA. What goes here? Well, the meet of A and A is just A. The meet of A and B is B. The meet of A and C is C, I mean the greatest lower bound. And so on, right? So you should be able to continue this table here. Let's do one more in the second row. For instance, BA, what goes here? Well, we take B and A, we see that the meet is going to be B. So we see that this table is going to be symmetric, right? It's the same, the greatest lower bound between A and B, than between B and A. B and B is going to be B. B and C, let's check this one. B and C, what goes here? We're talking about B and C. Well, we can see that the greatest lower bound between these is E. So we put E here. And so in that way we can complete all this table of the meet. We can do the same for the join, and also will help to have in mind to do these operations, the analogies or the particular cases that we have seen where the meet is actually the intersection, is this where subsets, and the union will correspond to the join. So that will be one of the examples that we have seen, and also in the example of the divisors of a number, we saw that the meet coincide with the greatest common factor, and the join coincide with the least common multiple. These things will help us in the right direction to do the calculations. So let's calculate a few of the join now. So for instance, A join A, I mean this one is going to be just A. Now A join B, so we have A and B. What is the least upper bound? Well, it will be A. Let's do, for instance, BD. Let's say BD is B here, D here. What is the least upper bound? So we go here, the least upper bound will be A. What is the join of, say, B and G? So let's say here B and G. So what do I put here? So B and G will go to the upper bounds, and the least upper bound will be A. So here will be A2. What about, for instance, say A and G? So let's look here, A and G. So the question is, what do I put here? So I look at here for the least upper bound, and it's C, so here will be C. So in that way you can actually fill all this table of operations for this particular lattice. Let's see the example now in which the lattice is smaller, so the tables of meet and join are going to be smaller too. And having in mind that the relation of order here is divide, so we know that this lattice with the operations meet and join is actually the same thing that calculating here the greatest common factor and here the minimum common multiple. So when we fill this table, we can be thinking that when we have to put here the meet, we were going to be thinking the greatest common factor. So we can say, for instance, 1, 1. The greatest common factor is 1, or we can see directly this in the Hasse diagram. So 2, 1 is 1, right? 2, 1 is 1. 3, 2. What is the greatest common factor between 3 and 2? Let's look at 3 and 2 is 1. We know that the greatest common factor between 3 and 2 is 1, right? So we put here 1. And so on, we can continue to construct all this table like this. So if we have, for instance, the greatest common factor between 6 and 3 is 3, right? So between 6 and 3, we're going to put 3. And so on, we can construct the whole table like that. So between 2 and 1 is 1. Every time that appears 1 here is going to be 1, right? Between 2 and 2 is 2. Between 2 and 3 is 1. Between 2 and 6 is 2. Between 1 and 3 is 1. Between 3 and 3 is 3. Between 3 and 6 is 3. And between 6 and 1 is 1, between 6 and 2 is 2, and between 6 and 6 is 6. Now let's complete the table for the join. That in the case of the relation division is going to be the least common multiple. So if I said what is the least common multiple between 2 and 3, well, it's going to be 6. Though I can see that thing also in the drawing, right, in the Hasse diagram between 2 and 3, the least upper bound is 6. So that's the 6 that I put here. And so in that way, I can complete the least common multiple between two numbers by just deciding what is the least common multiple or just looking at this diagram. So for instance, between 1 and 1 will be 1, between 1 and 2 will be 2, between 1 and 3 is 3, 1 and 6 is 6. See that every time that appears a 1, the least common multiple is going to be the other one. Between 2 and 1 is going to be 2. Between 2 and 2 is 2. Between 2 and 6 is 6. Between 3 and 1 is 3. See that the least upper bound is always an upper bound, so it's in the bigger side, let's say, of the numbers. So between 3 and 2 is 6. Between 3 and 3 is 3. Between 3 and 6 is 6. Between 6 and 1 is 6. Between 6 and 2 is 6. Between 6 and 3 is 6. And between 6 and 6 is 6. So we have a way then to construct these tables for the operations meet and join by either, if we know the meaning, by just calculate the least common multiple or the greatest common factor, Or we can just do that even without knowing what is the meaning if we have the Hasse diagram by calculating in the Hasse diagram what is the greatest lower bound and the least upper bound. So let's see in this very simple lattice. So this is a lattice in a set that has only two elements, false and true. That, as we have called those also in the logic, when we saw logic theory, this false and true, we can call it 0 and 1. So if I call 0 and 1, then I have an easy way to define this relation of order. I'm going to define this relation of order as less or equal to. As these are numbers, it makes sense to say less or equal. So I can say that f is less or equal than t, right? Because f is 0 and t is 1. So in that way, I can draw my Hasse diagram where I put f in the lower part because it's less or equal than t. Now let's look just at our Hasse diagram and let's try to construct the table of the meet. Remember that the meet is the greatest lower bound. So we start with f, f. So between f and itself, the greatest lower bound is f. Now between f and t, the greatest lower bound is f. So we write f. Now between t and f, the same thing, right? So remember it's going to be symmetric, so it's going to be f2. And finally, between t and t, the greatest lower bound is just t. So this is the table that we got for the operation meet. Think for a moment. Look at what we are getting here. False, false is false. And false, false is false. True, false, false. False, true, false. And true, true, true. As you may remember, we are getting nothing but the truth table for the operator AND. Let's construct this other table for the join. And so remember that the join is the least upper bound. So when we do f and f, the least upper bound is going to be f. When we do f true, the least upper bound is true. So we'll put a true here. When we do true, false, by symmetry, it's the same thing. We're going to go true, true. And when we do true, true, the least upper bound is going to be true. So let's look at the table that we got here. False, 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 true, 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 false. So that may remind you of the table of true for the operator OR. This is exactly what this table is. So this set here with this relation, we got a poset that have this Hasse diagram and these tables of operations that are nothing but the AND and OR tables that we have seen in logic. So this lattice with the operations meet and join is just with the operations AND and OR.